A very good evening to you all, and welcome to Module 7, Ethernet Switching of our CCNA Structured Training class. Module 7 is a continuation from Module 6, which is data link. When we talked about data link, we said it is the layer 2 of the OSI model. And we said that the data link layer has two sublayers. It has the MAC sublayer and the logical link control sublayer. Now, we also said that the MAC sublayer deals with the physical device, that is the physical layer, and particularly the network interface card, while the logical link control deals with the upper layer, particularly the network layer. Okay. Now, the device that functions at the data link layer is called the switch. Now, the technology that we'll be looking at is called Ethernet switching. Ethernet switching. So it's a continuation of the data link layer. Now, in today's class, is also going to be a brief class. We will be looking at Ethernet frame, and we'll explain how Ethernet sublayers are related to the frame fields. Remember, we said the PDU is known as frame in the data link layer. Okay. We'll also be looking at the Ethernet MAC address, and we'll be describing the Ethernet MAC address. We'll also be looking at the MAC address table, and we'll explain how switch builds MAC address table and forward all these frames. Okay. Then we'll be looking at switch speed and forwarding methods. Okay. There are certain types of methods that the switch does when it forwards packets, frames rather. So we're going to be looking at that as well. Okay. So let's look at Ethernet frames. Like we said, that the data link layer operates at layer 2 of the OSI model. And the data link has the logical link control and MAC. The MAC means media access control. When you say media access control, it talks about how you can access the media. Okay, and what media? The network media. And that's where the network interface card comes in. So it is a family of networking technology that is defined in the IEEE 802 standards, right? So when it comes to Ethernet encapsulation, it adds the header information, okay? And we will look at the header information in the data link very soon. Now, the data link has two sublayers, like we said yesterday, right? It has the logical link control and the media access control. So the 802 LAN-MAN standard, including Ethernet, uses these two separate layers. The logical link control, as you see, places information in the frame to identify which network layer, okay, because it relates with the upper layer. When it comes to the issue of encapsulation, let me so when it comes to the issue of encapsulation, at the network layer, it carries the network header information and sends down to the logical link control that controls it. Okay. And then that's what it does. So it relates with the upper layers. Now, in the media access control, there are certain protocols that governs, or technology that runs it. Okay, we have the various Ethernet standards for the fast Ethernet, gigabit Ethernet, and things like that. Because you'll see that the fast Ethernet runs at 100 Mbps, the gigabit Ethernet runs at 1000 Mbps and things like that. Then we have the 10 gigabit Ethernet. So that is controlled under MAC. Okay. Then in the media access control, it also talks about the wireless LAN. All right, where you have the various wireless LAN standard, that are used. Okay, so we also have the wireless private area network, and so the standards that work in that, especially things like Bluetooth, things like RFID, things like near field technology, and things like that. Okay, so all of those are managed at the that sub layer. So the MAC sublayer is responsible for data encapsulation and accessing the media. That is basic function, data encapsulation, and then accessing the media. So IEEE 802.3 data encapsulation include Ethernet frame, which is the internal structure of the Ethernet frame. Also Ethernet addressing. All right, the Ethernet frame includes both source and destination MAC addresses to deliver the Ethernet frame from the network interface card to the other network interface card, which is like the destination on the same LAN. And then it also has or handles what they call the error detection. Now, what it uses is the frame check sequence, sometimes called the FCS. How does this actually work? If you have a frame and the frame based on the header information says that the frame is 1000 bytes, for instance. So once you are sending the frame or you receive the frame, the FCS checks the size of that particular frame. If it is more or less than 1000 bytes as specified in the header information, it will flag it off for error. Okay. So the media access layer includes the specification of the different Ethernet communication standards over various types of media, including the copper media, the fiber media, and things like that. Remember, because this media access talks on how the device access the network medium. And in the network medium, remember we said we have three types. You have the copper, which is the electrical medium. You have the fiber, which is the optical medium. You have the wireless, which is the electromagnetic waves. So all these standards are defined over there. So the legacy Ethernet using a bus topology or hub is a shared half duplex medium. Ethernet over a half duplex medium uses a connection-based access method. Carrier sends multiple access collision detect. It uses that. And then additionally, the Ethernet LAN of today uses switches that operates in full duplex mode. All right. And when we say full duplex, we're talking about communication with the Ethernet switches as they do transmission and they do receiving at the same time. Now, in the header information of the frame, what are the different fields that you have in the frame? The minimum Ethernet frame size is about 64 bytes, and the maximum size is about 1518, that is 1518. So this is the size that it ranges, okay? So the preamble fields is not included when describing the size of the frame, but any frame less than 64 bytes in length is considered a collision fragment, or we call it sometimes a round frame, okay, and is automatically discarded. So anything less than 64 will be discarded. So frames that are also more than 1500 bytes are considered jumbo or baby giant frames. Okay, so if the size of the transmitted frame is less than the minimum or greater than the maximum, the receiving device drops this particular frame. So drop frames are likely to be as a result of collision or other unwanted signal. They are considered invalid. So jumbo frames are usually supported by most of the fast Ethernet and gigabit Ethernet frames and the network interface cards. Okay, so that particular size is very, very, very important. And that is why you see it is specified in the frame size. You have the preamble, which is about 8 bytes. You have the destination MAC address, which is about 6 bytes. You have the source MAC address, which is 6 bytes. You have the type and length, which is 2 bytes. Then you have the data itself. And within this data, it contains the initial data from the application layer, and it also contains the header information from the application, session, presentation, transport, network layer. Okay, so it contains all those other layer information. So all of it is placed inside this data, and it ranges between 45 to 1,500 bytes. Then at the end, it has what they call the FCS, which is the frame check sequence that checks for errors. Okay, checks for the errors. So let's look at Ethernet MAC address. Now, we said in the previous class that when it comes to layer 2, the addressing format uses MAC addresses. In layer 3, the addressing format uses IP addressing. In layer 4, the addressing format uses port addressing. So since in the layer 2, it uses MAC addressing, we need to understand how the switch uses this MAC address. And yesterday, we looked at the conversion into hexadecimal. MAC addresses are usually considered a 48 binary value expressed using 12 hexadecimal values. So it is represented in hexadecimal. So it has combination of letters, alphabet, and numbers. And those alphabets are within A to F. Okay. So given that 8 bits, which is 1 byte, is a common binary grouping, binary 0 into 8 places is like the minimum in binary, and the maximum you get is 11111 into 8 places. So that is what we have. The minimum value is 0. The maximum value in binary is 1111111 in 8 places. So in hexadecimal, this 000 in 8 places is 00. And the 11111, if you convert it to hexadecimal, you will get FF. So when using hexadecimal, leading zeros are always displayed to complete the 8-bit representation. For example, when you have a binary value, this like this is represented in hexadecimal as 0A. Okay, as 0A. So instead of you to just put A, because it can just be A on its own, it can just be 0A, right? So hexadecimal numbers are often represented by the value preceded by 0x, right? So that's how it's represented, and it's represented that way to distinguish it from decimal, so that you will know that this is hexadecimal documentation. So hexadecimal values may also be represented, by a subscript, where you put hex at the subscript, or you put H at the end. That is how it is represented. So in an Ethernet local area network, every network device is connected to the same shared media. Okay, the MAC addressing provides a method for device identification in the data link layer of the OSI model. So an Ethernet MAC address is a 48-bit binary address expressed in 12 hexadecimal digits because a byte equals 8 bits. And we can also say that a MAC address is 6 bytes in length. So all MAC addresses must be unique to the device, the Ethernet device interface. Why are we saying it must be unique? Because it was produced by the manufacturer, and the manufacturer created the MAC address for that particular device. So there's no two network cards that should have the same MAC address. No, not ever. Okay, different network cards should have different MAC addresses. So that MAC address that we know is 12 hexadecimal digits or 48 binary digit represent different things. So all MAC addresses must be unique, like we said, and to ensure that they are all unique, all vendors that sell Ethernet device register with the IEEE. And when they register with the IEEE, they are given a unique 6 hexadecimal value. And that is what we call the organizational unique identifier. Okay. The organizationally unique identifier, it's like a 6 binary hexadecimal digit that is only unique to that organization or that company or that vendor that is producing that particular network card. Okay, so every vendor has its own unique distinct. Then that vendor will now have its own MAC address that it will now assign to the number. So you see that the MAC address has 12 hexadecimal digits. The first 6 hexadecimal digits talks about the organizational identifier, while the last 6 hexadecimal digits talks about the uniqueness of that particular MAC address. So if or when you have a frame coming into the switch, how does the switch process it? So usually the switch is a forwarding device. So when it is forwarding a message to an Ethernet network, excuse me, sorry. When the device is forwarding a message to an Ethernet network, the Ethernet header will include the source address and the destination address. Okay, it will include both the source and the destination. And the idea of including the source and the destination is so that when the switch is processing that frame, when the switch is forwarding that frame, remember the switch is a forwarding device, it will be able to know the destination. So when a network interface card receives an Ethernet frame, it examines the destination MAC address to see if it matches the physical MAC address that is stored in the RAM. So if there is no much match, the switch or the device discards that particular frame. But if there is a match, it passes the frame up to the OSI model layers where this will be decapsulated. But I want us to note that Ethernet network interface card will also accept frames if the destination MAC address is a broadcast or is a multicast. Okay, that you should just take note. So any device that is the source or destination of an Ethernet frame will have an Ethernet network interface card and therefore a MAC address. So this includes workstations, servers, printers, mobile devices, routers, and so on and so forth. So anytime you see like this is a switch. This switch has a port that is connected to H1, has a port that is connected to H2, has a port that is connected to H3, has a port that is connected to H4. So each of these H1, H2, H3, H4, these systems host, they have their own MAC address, each one of them. So the switch here will build what we call a MAC address table. We'll build a MAC address table. So maybe the MAC address of host 1 will be included here. And then which port is host 1 connected to? Let's say port 1. All right. Then the MAC address of host 2 will be there, and you will see that host 2 is connected to maybe port 4. Then the MAC address of host 3 will be there, and then maybe host 3 is connected to port 5. So the same thing goes to host 4 and so on and so forth. So if a frame comes into this, the switch will now check the destination MAC address. And if it sees that this MAC address matches the information in the MAC table, belonging to probably H2, then the switch will now forward that particular frame through port 4. And that is basically how it does. So in Ethernet, we have different MAC addresses, and those will explain whether we have the concept of what we call unicast, multicast, and broadcast. Unicast is when you are sending a message from one to one. In other words, I know the destination IP address. I know the recipient of my message. So I write my frame or I write my letter and I include the destination MAC address. In this particular case, this is a unicast. So you see, this H1 says that I need to send a frame to the server. And then it has the MAC address and the IP address of the server. So you see the message comes to the switch will check its MAC address table, and it knows that this server is in port 2. Then it will now forward the frame directly to that. There is no problem. So the process that the source host uses to determine the destination MAC address is usually associated with an IP version 4 address, which is known. Okay, sometimes if he doesn't know it, we use what we call the ARP, which is Address Resolution Protocol. And this is just a protocol that helps to determine the IP address if the MAC address is known. Okay, so that is it. Now, another type of message is the broadcast. We have seen unicast, one-to-one. Broadcast is when you are sending message from one person to every person in the group, right? So like H1 says that I need to send data to all hosts on the network. So it's sending a broadcast. So what do you think will be the destination MAC address? Because your message you are sending is not to one person. You are sending the message to an entire group, all right? And so you are sending it as a broadcast. So because of that, there is always a broadcast address. Once you see FFFFFF, all the fields are F, that is a broadcast address. Okay, so it is flooded out all the Ethernet ports except the port that the traffic is coming in. As you can see, it is going out all these channels here, but except here. Okay, that is how broadcast works. So if the encapsulated data is an IP version 4 broadcast packet, it means that the packet contains a destination IP version 4 address that has all ones, okay, in it. And that is just it. So the concept of unicast, the concept of broadcast. And then there is the concept of multicast. In the concept of multicast is that you are sending a message from one person to selected within a group. So it's not to one person, it's not to all the people, but it's to selected devices within the group. So in that case, you are sending a multicast. So just as we have a MAC address for broadcast, we also have a MAC address for multicast. So the destination MAC address for multicast is 01005E. Once you see that at the beginning of the message, at the beginning of the MAC address, you know that it is a multicast address. So, and the encapsulated data is an IP version 4 multicast packet and sends a destination MAC address of 33 when the encapsulated data is an IP version 6 packet. But there are other reserved multicast destination addresses, that you could use when the encapsulated data is maybe not IP, such as STP and things like that. But for now, this is what we are using. Okay, so if they flooded out all Ethernet ports except the incoming port, unless the switch is configured for multicast snooping, this will not be forwarded by the router unless the router is configured, to send multicast address, multicast traffic. Now, let's look at the MAC address table under switching fundamentals. So a layer 2 switch, Ethernet switch uses a layer 2 MAC address to make forwarding decisions. It is completely unaware of the data or protocol being carried out in the data portion of the frame, such as the IP version 4 packet, an address resolution protocol message, or an IP version 6 neighbor discovery packet. So the switch makes its forwarding decision based solely on layer 2 Ethernet MAC addresses. Okay, so an Ethernet which examines the MAC address table to make forwarding decisions for each frame, unlike legacy Ethernet hubs that repeat bits out all ports except the incoming port. So when a switch is turned on, the MAC address is empty. And it's very important for us to understand. So if it is turned on and the switch is, the MAC address table is empty, how then does the MAC address table get populated? How does it get populated? Usually, how it gets populated is that if I have this switch here, and I have maybe a PC here, a PC here, a PC here, a PC here, which means I'm supposed to have at least 4 MAC addresses on this MAC address table. But I just powered the switch, so the MAC address table will be empty. So for it to forward, to populate or to build the MAC address table, what the switch does is that since it is a broadcast device, if this PC1 sends a frame and the frame is meant for PC4, for instance, this message comes into this switch. The switch is now going to send it to all the ports. It's sending a broadcast to all the ports because it doesn't even know the MAC address of the destination. So once it sends to all the ports, it say, hey, I am sending a message for PC4. All right, this is the IP address, but I don't even know the MAC address. I don't even know whatever. Who is this? Then it's going to, when PC4 responds, as PC4 is responding, then the MAC address table will be built for port 4. Yeah, maybe PC4 is plugged into port 4. So maybe port 4 and then the MAC address for the PC4 there. Once it sends it, the source device also records its own MAC address. So maybe PC1 is in port 1. All right, it's in port 1, and then it puts like that. So that is how it keeps building, all right, until it's able to build a complete MAC address table. And that's why if you have a managed switch, it's not always good to always just power it off all the time like this, because each time you power cycle the switch, it generates a MAC address that we call it MAC address storm or broadcast storm. Okay, it will keep sending this broadcast each time you switch it. Now, another thing it does is that the switch does what we call learning and forwarding. And each frame that enters a switch checks for a new information to learn. It does this by examining the source MAC address of the frame and the port number where the frame is entered. Okay, so if the source MAC address does not exist, it is added to the table along with the incoming port number on that particular table. All right, so this is the port number, this is the MAC address. So once it takes in the source, it's going to put the port number of the source and the MAC address of the source. That is what it does. Okay, so sometimes it can find the destination MAC address as well. So if the destination MAC address is a unicast address, the switch will look for a match between the destination MAC addresses of the frame and the entry in the MAC address table. If the destination MAC address is in the table, it will forward the frame out the specific port. If the destination MAC address is not in the table, the switch will forward the frame out through all the ports except the incoming port. So this is called the unknown unicast. But if the destination MAC address is a broadcast or multicast address, the frame is also flooded out through all ports except the incoming ports. Okay, so as a switch receives frames from different devices, it is able to populate the MAC address table by examining the source MAC address of every frame. So when the MAC address table of the switch contains the destination MAC address, it is able to filter the frame and forward out through single port. So this is what we have been saying, that this switch has a MAC address table. And this guy, PCA, is sending a message because it is the source is going to look at this message is going through port 1. So it's going to record on port 1, then it will take the MAC address of PCA, which is this guy here. So you see, this MAC address is this one here. Then the message is destinated for PC4, which is D. All right. So once the message gets to D and D is sending an acknowledgement, then the MAC address table will record for port 4, host D. The MAC address of host D will be recorded in the table. So this is how it will continue to do until it builds the MAC address table of all the ports that are actually there. Let's look at switch speeds and their forwarding methods. So switches use one of the following forwarding methods for switching data between network ports. It uses what we call store and forward switching, and then it uses what we call the cut-through switching. Now, if you look at the names recycle, it says store and forward, which means it's going to store something and then before it forwards it, because the switch is a forwarding device. So the frame forwarding method receives the entire frame and it will compute the CRC. The CRC is the cyclic redundancy check. Remember, we said that the frame has a trailer or a trailer. Now, the trailer is the one that checks for errors. What kind of errors? It checks the size of the frame and compares it with the size as indicated in the header. So if the size matches, fine. So in the store and forward, is saying that a node will have to receive the complete frame first before it begins to forward it. Complete, checks for errors, and then it forwards it. But the other type is called the cut-through switching. And this frame forwarding method forwards the frame before it even reaches the before it receives the entire frame. All right. So what it does is that it looks at the minimum size of the frame. And remember, we talked about the minimum size should be 64 bits. So if it receives up to 64 bits, then it's going to begin to forward the frame. That is what cut through is saying. So it doesn't need to wait, for the whole frame to be received. So in the store and forward, it's a little bit slower, but it has some guarantee. All right. But the cut through is faster, but there is no guarantee. So a big advantage of store and forward switching is that it determines if the frame has errors or not before it begins to propagate the frame. And when an error is detected in the frame, the switch discards that particular frame. So discarding the frame with errors reduces the amount of bandwidth that is being consumed by data on that particular switch. And then you have the store and forward switching that is required to use quality of service, that is the QoS, all right, on a converged network where frame classification for traffic prioritization is actually necessary. Now, looking at cut through, it says in the cut through switching, the switch will act upon the data as soon as it is received. The moment it receives it, it begins to act on it. And even if the transmission is not complete, the switch buffers just enough of the frame to read the destination MAC address so that it can determine which port should be forwarded out the data or not. The switch does not perform any error checking on that particular frame because it does not wait for the entire frame to be released to receive. As soon as it receives the first 64 byte, what is there in the first 64 byte? It contains the destination MAC addresses, the source and the destination MAC addresses. All right. So under the cut through, it also have two modes or two variants. We have what we call the fast forward switching, and then you have the fragment-free switching. In the fast forward switching, it offers the lowest level of latency. That means it's very, very, very fast. Immediately forwarding the packet after reading the destination address. So because fast forward switching starts forwarding before the entire block has been received, there may be times when packets may be where packets may be relayed with errors. So the destination network interface card discards the faulty packet upon receipt. So fast forward switching is a typical cut through method switching. The other part of the cut through is the fragment free. And in the fragment free, a compromise between the high latency and high integrity of the store and forward switching and the low latency and reduced integrity of the fast forward switching. The switch stores and performs an error check on the first 64 bytes of the frame before it begins forwarding, because most network errors and collisions occur during the first 64 bytes, and it ensures that a collision has not occurred before it begins to send the frame. Okay, so those are the variants: fast forward switching and the fragment free. Those are the variants of the cut through. Okay, now what does memory buffering on switching mean? An Ethernet switch may use a buffering technology to store frame before forwarding them or when the destination port is busy because of congestion. Okay, so if we have what we call port-based memory, meaning that there's a memory in the port itself. So frames store in queues that are linked to specific incoming and outgoing ports. So a frame is then transmitted to outgoing ports only when all the frames ahead in the queue have been successfully transmitted. And sometimes it is even possible for a single frame to delay the transmission of all the frames in the memory because of the busy destination port. So the concept here is that there is a memory in the port. Then you have the concept of the shared memory. And in the concept of the shared memory, the memory is not resident in the port. It's resident in the switch, where all the ports actually share that memory that is there. So deposit all the frames into a common memory buffer that is shared by all the ports in that particular switch. Okay, so the frames in the buffers are dynamically linked to the destination port, which enables the packet to be received, on one port and then transmitted on another particular port. How about the duplex and speed settings? When we talk about duplex, we are talking about speed and bandwidth. All right, we're talking about how the devices will communicate with each other. So two of the most basic settings on a switch are bandwidth and duplex. All right. And it is critical that the duplex and bandwidth settings match each other, especially when you have two switch devices that are connecting one to another. So the duplex settings explains how the traffic moves. Full duplex is saying that both ends of the connection can send and receive simultaneously at the same time. Half duplex is saying that only one end of the connection can send traffic at the same time. But sometimes, like we said, auto negotiation is an optional function that is found in most Ethernet switches and even network interface card. And what does it do? It helps the two devices to automatically negotiate the best speed or duplex capacity or capabilities that are there. Now, duplex mismatch sometimes happen and is very common in fast Ethernet switches or maybe Ethernet switches. What I mean is that switches that runs on 10 Mbps or 100 Mbps. So it occurs when one port on the link operates a half duplex while the other port operates a full duplex. So once you have that, you always have duplex mismatch. All right. So you have switch one, for instance, saying that I am full duplex and I can send whatever I want. While switch two on the other side is saying I am half duplex, so I can only send when the link is clear, but I'm also getting a lot of collision. So when you have that, then you know that there's a problem. Okay, so it also can occur when users configure one side of the link and forget to configure the other side. So both sides of the link should have auto negotiation on, or both sides should have it off. So best practice is to configure both Ethernet switch ports as full duplex. Finally, auto MDIX. All right. The connections between the devices, once required, the use of either a crossover cable or a straight through cable. Remember in our last class, I think it was last class or the previous class, we talked about crimping and we talked about straight through cable and we talked about crossover cables. And we said that the straight through cables are meant to connect, what do we call it now? They're meant to connect unlike devices, while crossover cables are meant to connect like devices. So this auto MDIX actually helps in conversion. Okay, so if I'm using a straight through instead of a crossover and auto MDIX is configured, the device will automatically adjust its own setting so that the transmission can go on, even though I'm using the wrong cable. So most switch devices now support the auto MDIX. What is auto MDIX? It's automatic medium dependent interface crossover. Okay, so when it's enabled, the switch can automatically detect the type of the cable that is attached to the port and configures the interface accordingly. So the auto MDIX feature is enabled by default on most switches that are running version 12 and above, right? However, the feature could be disabled. For this reason, you should always use the correct cable type and not rely on auto MDIX feature. So this is what we are going to be looking at on the concept of Ethernet. So I'm going to open up the mic now. If you have question, you will ask your question. And while you are asking your questions, you will be signing your attendance. All right. So if you have a question, you just raise your electronic hand and then I will attend to you.